Welcome to Lecture 3.2, Symmetric and Skew Symmetric Multilinear Forms. Loosely speaking, linearity means we can pull apart sums and constants. In the last section, we studied linear maps from vector spaces X and U. So these were, in some sense, vector-valued linear functions because we inputted a vector X and we got out a vector U. And in this section, we're going to mostly focus on scalar functions. We have seen examples of this, such as dual vectors, which are linear scalar functions from X to K. We have seen our scalar product notation, which is L comma X, or L of X. Now this is technically a bilinear function, and it's a function from the direct product of the dual of U and X to K. And this is why I said loosely speaking above, because we've talked about not just linear scalar functions, but bilinear functions as well. And you've likely seen linearity in other contexts, in other classes. Determinants are things that you've hopefully have seen in your undergraduate class, but these are functions. They can be thought of as functions on n vectors, either row or column vectors, where we can break apart certain sums and pull out constants. Now we can't just pull out constants any way we want to. It's not true that the determinant of C times A is not equal to C times the determinant of A, but we know that we can pull apart constants from individual columns. So once again, all of these involve some linearity. These are what are called n-linear functions. These are bilinear, these are linear. And again, linearity appears in all of these because there is some sense of how we can pull apart sums and constants. All of these are examples of multilinear functions. If we specify the particular argument, then we might call it a k-linear function. And the k-linear scalar functions are often called k-linear forms. I don't know exactly why we use forms instead of functions. I'm sure it comes maybe from differential forms. I tried Googling it, and I didn't get a simple answer. So anytime you see k-linear or multilinear form, you can think of it as a k-linear or multilinear scalar function. In the previous lecture, I showed you how the determinant is actually a property of a linear map, not a matrix. In this section, we will define and study the determinant in this more abstract context. Now, I told you what it was unofficially in the previous lecture, but we are going to formalize it using these n-linear forms. The set of all k-linear forms on X, so here I'm requiring that all of the inputs are the same, say unlike up here, and also that the dimension of X equals n, is a vector space of dimension n to the k. We've seen this up here for the dual space. This is a set of one linear forms, and it is a vector space of dimension n to the first. There are several important subclasses of k-linear forms that are subspaces of this space, namely the symmetric k-linear forms, the skew symmetric k-linear forms, and finally the alternating k-linear forms. We will introduce the first two of these in this lecture, and then the next lecture will be on alternating k-linear forms. Here's the formal definition. Now, I'll often do this. I won't define what all of these terms are because I think it should be clear from the context. So clearly, all of these are vector spaces. We can assume that they are finite dimensional, and all of them are over the field K. Okay, so a k-linear form is a function f from the direct product of k vector spaces to the field they are over that is linear in each coordinate. That is, if we fix all but one of the inputs, then f is linear in the remaining input. Now, unless otherwise stated, we will always assume that all of these factors are the same vector space, and we'll call that X. Now, that's not always the case. We've seen that the scalar product notation of L of X is a bilinear form from U prime cross X to K. Examples of this include one-linear forms, which are just the linear scalar functions in X. Two-linear forms are bilinear forms. A three-linear form is a function that takes three inputs and spits out a constant. Let me give you an example of what this will look like. So suppose we have an input, say a1 x1 plus a2 x2 in the first coordinate, and then y and z. So f of this, remember we can pull apart sums and constants. So that means we can always write this as a1 f of x1 y z plus a2 f of x2 y z. So notice that if I ignored the second and the third coordinates, then f is linear in the first coordinate because of this relation. Now, if we don't specify the k, if we just know it's a general form, then we will call it a multilinear form. Now we come to the result that I mentioned earlier, which is if X is an n-dimensional vector space, then the set of k-linear forms on X is a vector space of dimension n to the k. Now, I'm not going to give a formal proof of this because there's a lot of details which are very straightforward to check. Like, I'm not going to check the vector space axioms. I'll let you do that. And for the dimension, I'm going to actually just show you what a basis is, and I'm not going to check all the details and verify that it is a basis. But I think once you see it, you'll be convinced. Okay, so first thing to do is let's start by taking a basis for x. So let's let x1 up to xn be a basis for x. And now what I want to do is I want to motivate this by looking at the dual basis. So this is going to have a dual basis. L1 up to Ln is the dual basis. And let's think about what this, or how this is defined. So remember, that means that Lj of xi equals 1 if I equals j, and 0 if I does not equal to j. Okay, so now let's look at a bilinear form. So before I tell you the dimension, I think I'm going to give you an example, or before I tell you a basis of this space, and actually I haven't even given notation for this space. Let me do that now. I don't think we're actually going to use this notation again, that's why I don't have it, but one notation that some people use is script t, so tk of x prime. So this is like think of it like a k-fold generalization of the dual space. Okay, so let's do an example. So if n equals k equals 2, so let's look at this set of bilinear functions f from x, so x cross x to k. And of course the basis is x1 and x2. So now a bilinear function is going to have the form f of uv. So if we have two inputs, we can write those inputs using our basis. So a1 x1 plus a2 x2. And b1 x1 plus b2 x2. Now we can use bilinearity and break this up. So let's treat this second term as a constant. Ignore that and look at the first coordinate. So we can write this as a1f of x1 b1 x1 plus b2 x2. And then the next one is going to be a2 times f of x2, and then b1 x1 plus b2 x2. Okay, now we can do the same thing with this second coordinate. Now we could have done that all at once, but I think it helps to do it one by one when you're first learning this. So this is going to be a1 b1 times f of x1 x1 plus a1 b2 f of x1 x2 plus a2 b1 f of x2 x1 plus a2 b2 f of x2 x2. So what I want you to notice is, in some sense, these four things are, so if we have an unknown function f, then once we specify these four things, that will specify the entire function itself. As the AIs are determined by u and v. So in other words, a generalization of this is the following set. So how about if I just list them? F1 1 of xi xj. So let's define this to be the set, or let's define this to be the function, which is 1 if this is x1 and this is x1. So if x1 and x2, let's say that differently. If I and j are equal to 1 and 0 otherwise, and then we'll say that f12 of xi xj, this is going to be 1 if I equals 1 and j equals 2 and 0 otherwise. So in other words, this is going to be 1 if xi is equal to x1 and xj is equal to x2, then this will give me 1, and for all other combinations of basis vectors, I get 0. Now I'm not saying it's 0 for all other vectors, because obviously if I have 2x1 and 2x2, it's not going to be 0, but for all combinations of basis vectors. Now we have f21 of xi and xj, so this is going to be 1 if I equals 2 and j equals 1 and 0 otherwise. So if x2 and x1 go in here, I get 1, otherwise I get 0. And then f22 of xi and xj, this is going to be 1 if I and j are equal to 2 and 0 otherwise. Okay, so I claim that this is a basis of my set of bilinear functions. And again, I'll let you check the details, but I think you should hopefully make sense why these. So once I define these four things, I've completely defined f. These are my degrees of freedom. Now to build off this example, this is where n and k is 2. I think it's helpful to see one where n and k are 3 and 2 and 2 and 3. So let's start with how do I want to do this? When n equals, so n is the dimension, let's say n equals 3 and k equals 2. In this case, f of uv is f of a1 x1 plus a2 x2 plus a3 x3 and b1 x1 plus b2 x2 plus b3 x3. And if we do the same thing, what we're going to get is we're going to get, how about if I do it like this? Just some constant times f. Now we have all combinations, so x1, x1, 1, 2, 1, 3. So we're going to get f x1, x1 plus constant times f x1, x2 plus some constant times f x1, x3 plus some constant times f times x2, x1 plus f of x2, x2 plus some constant times f x2, x3, and finally plus something times f x3, x1 plus f x3, x2 plus something times f x3, x3. Now, a general n linear form, or sorry, general bilinear form here for n equals 3 is, now I'm saying this a little differently than what I did over here, but just for a general one, these constants can be anything they want. So for example, let's call this one C11, C12, C13, C23, sorry, C21, C22, C23, C31, C32, C33. And I know this is different than what I said up here, because here I said, well, we can fix these to be anything you want. And here I'm saying, well, let's let the constant change. Now, I actually am being consistent. Compared to the dual basis, a general element, going back to here, a general element in the dual space is of the form L, so is a linear combination of these things. So L we think of as A1, A2. Think of the row vector up to AN. So what this means is this is literally A1, L1 plus A2, L2 plus AN, LN. So we're taking a linear combination of these dual basis vectors. That's what we're doing here. Just now we have think of it like a two-dimensional linear combination, or we have 9 of these things, or we're taking this linear combination of these 9. So this is like the two-dimensional analog. I don't want to say dimension. It's like the two-parameter analog of what we're doing up here. Okay, so we'll do one more of these, and then I will write down the general formula. So if n equals 2 and k equals 3, now this is one where we have f of u, v, w. So this is going to be f of a1x1 plus a2x2, b1x1 plus b2x2, and c1x1 plus c2x2. So if we multiply this out, now what we're going to get, think about how this is going to be different. Now we're going to have 3 terms. So we're going to get something times f of x1, x. So we're going to get for every one of these inputs. So when we break these things out, we're going to get one of these basis vectors in here, one in here, and one in here. So f of x1, x1, x1 plus something times f of x, say, how do I want to order this? x2, x1, x1 plus something times f of x1, x1, x2 plus something times f of x2. Maybe I could have done this better. Oh, well, x2, x1, x2 plus something times f of x1, x, now what am I missing? x2, x1 plus something times f of x2, x2, and x1, and so forth. You get the idea. So I'm going to call this C11, sorry, I'm going to call this C211. I'm going to call this C112, C212, C121, C221. And now let's compare. Up here we have the dimension of this space is going to be n to the k, which is 2 to the 2, which is 4. You can see we got 4 of these. Down here, the dimension of this space is going to be n to the k. So n now is 3, so that's 3 squared is going to be 9. And down, because you can see we have 9 possibilities for Cij. And now here we have 3 subscripts, but there's 2 possibilities for each. So you know what? I can finish this because I'm close enough. So we also have f. Okay, so now what am I missing? F of x1, x2, x2 plus something times f x2, x2, x2. So now we have C122 and C222. So clearly the dimension up here, the dimension of this space is n to the k, which is now 2 cubed, which is 8. So we have eight possibilities here. So for all of this, we're going to really think about how this generalizes what we have up here. And now let me give you, without proof, the basis for general k-linear forms. So I think the hardest part about this is the notation. So the basis of this is going to be the set of all, I'm going to call it fj1 up to jk. This is not the product of those. This is sort of like, I'm just not putting commas in, like, oh, I don't have commas in here. So a basis for this are the following functions. So these things are all functions of k inputs, where these are not just arbitrary vectors, but we can define them on inputs of the basis vectors. And this is going to be equal to delta I1J1, sorry, I should put the dots up here, times delta of IKJK. And this ranges from 1 up to n, each of these. Now, what is this saying? So first of all, these are Chronicler Deltas. And remember what a Chronicler Delta is? Not from this class, but I think it's just a general thing that comes up in a lot of parts of math, is it's 1 if p is equal to q. So delta pq is 1 if p is q, and 0 if p is not equal to q. And I'm not telling you what the domain of this is. You know, these could be integers or real numbers or something. But the point is that this evaluates to 1 if the two entries are the same, otherwise 0. So the product of these things mean that the only combination of input vectors for which this evaluates to 1 is when all of these Chronicler deltas is 1. In other words, this evaluates to 1 if and only if j1 equals I1, if j2 equals I2, all the way up to jk equals ik. In other words, if this input matches that input, and if that input matches that index, I should say. So on all of the combinations, we're going to get 0, except for the one specified by this string of numbers right here. So notice that is exactly what we are basically doing down here. And I think it's maybe a better way to see this is a direct generalization of the dual basis and this definition here. Just now, instead of a j and I, now we have we have k entries, and what we're doing down here is really taking linear combinations of those, and that's analogous to linear combinations of this. Now, at last, we come to the topic which is actually the name of this lecture. That is the symmetric and skew symmetric multilinear forms. So if f is a k-linear form, then for any permutation of k elements, think of the k entries, we can define a new k-linear form, pi f. And that's basically what you get from our old k-linear form by permuting the entries according to pi. A k-linear form is symmetric if it doesn't matter how you permute the entries, you get back the same thing. A k-linear form is skew symmetric if any time that we transpose two entries, the sign sign flips. Let's finish with some examples of these. I'll start with symmetric ones. So one of the most common ones is the dot product. So I'll call this example 1, the dot product. So this is f of, let's say, a1x1 plus anxn, b1x1 plus bnxn. So this is just a1 b1 plus, say, a2 b2 plus all the way up to an bn. So this is a symmetric bilinear form because we have two entries. Now notice that if we let L1 up to Ln be the dual basis, then what this thing basically is it is equal to L1 of x1 times L1 of x2 plus Ln of x1 Ln of x2. So let me do this in 2 dimensions, just as a special case of this. So if we have f of x, because I'm going to generalize this. Now I should say there's nothing special about L1, these being the dual basis vectors. We can let the Li's in here be any linear function. And if we define it, we can define a bilinear function as a sum of Li x1, Li of x2 for I equals 1 up to n. And here, these don't have to be the dual basis vectors, just any scalar functions. So for n equals 2, f of, let me try this again, a1 x1 plus a2 x2 and b1 x1 plus b2 x2. So you can think of this as in vector form, a1, a2, b1, b2. So the standard dot product is what you get by multiplying, this times this plus this times this. But you can do like a twisted dot product. You could multiply a1, b2 and a2, b1. So let's do that one as well. So this isn't actually a special case. Decided to do something different. So here's one, a different symmetric bilinear form. A1, A1 B2 plus A2 B1. Now in terms of the dual basis vectors, what is this? This is L1 of x1 times L2 of x2 plus L2 of x1 times L1 of x2. So this is a symmetric bilinear form. Let me modify this to get a skew symmetric bilinear form. So I'll go down here, skew symmetric. So if we change this plus here to a minus, and we write L of, how about if I say this, f of A1, A2, and B1, B2, I think this is a little bit easier to visualize, is A1, B2 minus A2, B1. So in general, this is L1, X1, L2, X2 minus L2, X1, and L1, X2. And once again, this holds not just for the specific Li's that are the dual basis vectors, but for any linear functions. If I replace these L1s and L2s with the general L and M, this will be skew symmetric as well. Okay, other examples of symmetric bilinear forms. I don't really have too many left. I guess one you can do is, if you have it for a k-linear form, if you want to make it symmetric, if you have any k-linear form, you can add up over all, I'll call this pi, over all permutations in Sk, pi f of x1 up to xk. In other words, for k equals 3, if you take f of x1, x2, x3 plus f of x1, x3, x2 plus f of x2, x1, x3 plus f of x2, x3, x1 plus f of x3, x1, x2 plus f of x3, x2, x1, this is by definition going to be symmetric, because no matter how you permute these entries, you're going to get the same thing. So this is a symmetric k-linear form. I'm trying to think what else. Let's do so this is going to be symmetric. We can modify this to be skew symmetric if we take f of x1 all the way up to xk, and now we add up for all permutations. How about if we do pi f of x1 all the way up to xk, but we take the multiply by the sign of pi. So if we have an even permutation, it's a 1. If we have an odd permutation, it's a -1. So I'm not going to verify that this is skew symmetric. I will let you check that if you want. But this is a way that we can generate skew symmetric forms. Okay, so in the next lecture, we will look at another class of k-linear forms, which are called alternating. And these are actually, it's very similar to skew symmetric forms. And these are actually what determinants are. So that's going to be key to define the determinants formally. So stay with us.